Welcome back. Imagine for a second that you are the lead flight director on a multi-billion-dollar space mission. Everything is on the launch pad, the countdown is running. In that room, there is absolutely zero margin for error. Every single calculation, every input, every automated process, and every output must be flawlessly executed, or the rocket simply doesn't launch. Well, treating your Cambridge computer science exams with that exact same level of precision is exactly what we are talking about today. Whether you are taking the 0417, 0478, 0983, 0984, 2210, or the advanced 9618 syllabus, you need a bulletproof strategy. We're going to dive deep into mastering pseudocode, specifically the input, process, and output cycle. To kick things off, I want to introduce you to two types of students I see all the time. Let's call the first student Alex. Alex is incredibly smart but overloads every single answer with raw computer science facts, just dumping textbook definitions onto the page without any real analysis of the specific problem. Then we have Sam. Sam understands the logic but rushes. Sam completely misses the specific command word requirements in the prompt, writes a sloppy loop, and leaves easy marks on the table. Both of these approaches lead to massive point deductions, and we are going to fix that today. We are going to show you how to build an exam strategy that guarantees a perfect lot. Here is the exact roadmap we are going to use to get inside the examiner's mind today. We'll start with Section 1, the pseudocode problem. Then, Section 2, the core theoretical principles you need to know. Section 3 introduces the method mark strategy. Section 4 is our systematic processing sequence. Section 5 covers evaluating algorithm quality. And finally, Section 6 will hit the top examiner warnings. We are going to break down the methodology, the theory, and the specific pitfalls that separate a totally average passing grade from those top-tier elite academic performances.
Section 1. The pseudocode problem and why it is genuinely so difficult for so many candidates. To start, we really need to address a high-stakes reality regarding how students like Alex and Sam approach this topic under exam pressure. Look, pseudocode isn't just about throwing random variables onto a page and hoping they somehow compile in the examiner's mind. It just doesn't work that way. It is a highly structured, incredibly precise language of logic. Bridging that massive gap between a plain English problem description on your exam paper and a fully functional computational solution is exactly where so many candidates completely stumble. When Alex sees a problem, Alex just writes down everything they know about arrays and loops, hoping the examiner finds something worth a mark. When Sam sees it, they skip the planning phase and jump straight into writing messy code that doesn't actually answer the prompt. We need a system to stop this from happening to you.
I want you to really absorb this direct warning from the Cambridge senior examiners. They state, examiners report that writing pseudocode with input, process, and output is one of the most misunderstood areas in computer science. This isn't just a tiny hiccup that a few students face. It is a massive, systemic misunderstanding recognized right at the absolute top by the people grading your papers. This quote brilliantly illustrates exactly why we need a totally systematic approach to our algorithms. If you don't have a system, you are just guessing. And we don't guess when we are preparing for Cambridge exams. We engineer success.
Section 2, core theoretical principles, building your foundation. Let's move to the underlying theory and see how the assessment framework is actually built behind the scenes. Before you write a single line of pseudocode, you really have to understand the specific rules of the game you are playing. This is where we introduce the ultimate game changer, decoding command words. You need to know the difference between a prompt that asks you to state, one that asks you to describe, and one that asks you to evaluate. And once you decode that command word, you need a framework to answer it. We use the PEAL framework. That stands for point, evidence, explanation, and link. Every time you write an extended answer about an algorithm, you make your point, you provide your pseudocode or data as evidence, you offer an explanation of how it works, and you link it back to the specific exam scenario.
Let's look at how the examiners are actually judging you. Every single question is purposefully designed to test 3 distinct cognitive domains. These are knowledge and understanding, application, and analysis. This means raw knowledge alone, like Alex's strategy of just memorizing facts, will never secure top marks. If you merely memorize the syntax for an input statement, you've only hit the very first domain. You have to be able to apply that specific syntax to a totally novel scenario, and then deeply analyze your own logic to ensure it actually solves the problem presented. You need all 3 domains working in perfect harmony.
The absolute crucial takeaway here is that Cambridge academic benchmarks heavily reward logical, structured reasoning over simply listing surface-level facts. We are talking about superficial breadth versus analytical depth. Superficial breadth, which is just showing you know a lot of random computer science terms, will actively lose you marks. Analytical depth, applying the Peel framework to dive deep into one specific solution, will gain you those top marks. The theoretical architecture of this syllabus rests on precise definitions, understanding causal relationships, and integrating your answers. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, as I was saying, candidates who reference cross-topic connections and show deep analytical depth achieve significantly higher marks every single time. It is all about the depth of your reasoning.
Section 3. The method mark strategy, rewarding the process. Now, what is genuinely really interesting about this next concept is how it acts as an incredible safety net. It completely relieves the pressure of needing a flawless, perfect final algorithm on your very first try. Think of this as the backup systems on our space mission. Even if the primary system has a glitch, the mission doesn't immediately fail.
Let's look closely at the definition here. The method mark strategy is a grading framework where examiners actively award marks for demonstrating the correct analytical process and working steps, even if your final output has minor flaws. By understanding this, you can completely maximize your score by proving your systematic processing rather than just obsessing and freezing up over the final code execution. Let's think back to our students. If Sam slows down and writes out the logical steps clearly, but makes a tiny syntax error at the very end, Sam is still walking away with the vast majority of the points. Why? Because the working clearly shows an understanding of the input, a correctly structured process, and a logical attempt at an output. The examiners want to reward your analytical journey. You just have to show it to them.
Section 4. Systematic Processing Sequence. This is your procedural blueprint. To reliably capture every single one of those method marks we just talked about, we absolutely need to implement a standardized sequence for every problem. You should never, ever go into a Cambridge exam hoping for a sudden flash of inspiration. You need a rock-solid step-by-step procedural blueprint that you can execute flawlessly under pressure. We call this the Computer Science Success Blueprint.
Let's break down the 5 exact steps of this blueprint. Step 1. Deconstruct the question. This means aggressively circling the command words, so you know exactly what the examiner wants. Step 2. Extract relevant data. Pull out the precise inputs you are given. Step 3. Select your analytical framework. Are you using a for loop? A while loop? Make that decision before you write anything. Step 4. Execute with clear notation. Write your pseudocode neatly. Step 5. Present with correct terminology. This is where you use the Peel framework if you need to explain your logic. If you meticulously follow these exact 5 steps when tackling past papers, you establish an evidence-based reasoning chain. You transform from a student who guesses into a candidate who engineers the perfect answer.
Stop scrolling! Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's jump straight into Section 5, Evaluating Algorithm Quality and Developing the Top Scoring Mindset. We are entering our interactive workshop phase right now. I want you to imagine a highly complex computer science data table tracking user inputs on a server. If I gave you exactly 60 seconds right now to scan that data, what would you look for? Top-tier students don't just stare at the numbers, they immediately look for the core trend. They look for anomalies. They push past a passing grade by actively evaluating the data, not just passively reading it. Top-scoring candidates demonstrate this evaluative thinking in 4 very distinct ways. They constantly consider multiple solutions. They analyze the trade-offs of their code. They are not afraid to acknowledge the limitations of their algorithms, and they always justify their decisions with solid evidence. Time for challenge number 2. Let's play Find the Flaw. Imagine a student writes this sentence in an exam. I used a linear search because it finds the data. What is the massive flaw there? It loses marks because it lacks any analytical depth. It doesn't use the PEL framework. A top-scoring candidate would say, I used a linear search because the data array is unsorted. While a binary search is faster, it requires pre-sorted data, making linear search the most efficient choice for this specific, unsorted context. Do you see the difference? You have to embrace the deconstruct, solve, evaluate model. Show the examiner you know exactly why you chose that specific computational path.
To write those perfect answers, you need a framework for evaluation.
Always verify your results by checking how these 4 specific factors impact your algorithm: time complexity, space complexity, edge cases, and the overall effect on performance. Now for challenge number 3. I want you to do some speed writing in your head. Imagine you have 30 seconds on the clock. How would you write one perfect Peel paragraph explaining why checking for edge cases is important? You'd start with your point: edge cases prevent system crashes. Your evidence: an input of 0 in a division operation. Your explanation: the algorithm must process this without a fatal error. And your link: this ensures the specific banking application in the prompt remains stable. Addressing these essential evaluation criteria within your reasoning is the absolute hallmark of an A-star candidate.
Section 6. Top examiner warnings. Avoiding the pitfalls. Finally, we need to look closely at the principal examiner reports. Knowing what you should do is really only half the battle. Uncovering the easiest, most common ways candidates throw away points and knowing how to actively avoid those traps is what truly guarantees your success on exam day.
The examiners have isolated the top 3 mistakes candidates make year after year. Number 1 is confusing cause and effect. Number 2 is completely forgetting to check boundary conditions and extreme edge cases. And number 3 is giving generic answers that are not specific to the context provided in the question. This is exactly what Alex does. Alex writes a beautiful, textbook-perfect algorithm for a generic database, but completely ignores that the exam question specifically asked about a real-time weather monitoring system. You absolutely cannot write a generic algorithm you memorized at home. Your logic, your variables, your entire approach must perfectly match the unique scenario presented on that specific paper.
Let's really drill down into that most common terminology error because it is a silent killer of grades. You must be completely 100% precise about the difference between a cause and an effect. The cause is the input or the triggering condition. The effect is the resulting process or the final output. If you mix these up in your pseudocode or if you swap them around in your written explanations, the examiner's logic chain instantly breaks. And the second that logic chain breaks, your marks drop off a cliff. Precision in your language reflects precision in your coding.
I want to draw your attention to this direct, flashing red examiner alert. Candidates consistently confuse key terminology. Always define terms before using them in extended responses. Let this critical rule burn into your memory. This is where our 3 golden rules come together. Rule 1, command word decoding. Know what you are being asked. Rule 2, Peel framework application. Structure your extended answers properly. Rule 3, the time management matrix. Don't be like Sam, don't rush and skip defining your terms. Defining your terms first acts as a massive anchor for your analytical depth. It proves to the examiner before you even write a single line of pseudocode that your foundational knowledge is absolutely rock solid.
I am going to leave you with this highly provocative question straight from the senior examiners to really test your foundational knowledge before you tackle your next practice paper. Why do students find interpreting complex binary representations so hard? Think deeply about how that ties into input processing and consider exactly how you would break that complexity down systematically using the blueprint we discussed today. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here is your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the absolute biggest challenge you are currently facing with pseudocode. Our team responds to every single comment. Like and share this video with a study partner right now. Keep analyzing, keep refining that procedural blueprint. Ace the Exams, your Cambridge success starts here. I'll see you in the next one.